Good day everyone, my name is Dario Guidotti from the University of Sassari, and in this presentation I will discuss some of our recent work on the formal verification of autoencoders used for predictive maintenance within industrial applications. As you are likely aware, neural networks have been successfully applied across various domains within computer science. Nevertheless, their deployment in safety and security critical contexts remains somewhat limited due to the absence of formal guarantees regarding their behavior. Furthermore, since 2014, neural networks have been demonstrated to be susceptible to several reliability issues, the most notable being their vulnerability to adversarial perturbations. To address these concerns, our research explores how formal verification can be utilized to certify and enhance the reliability of neural networks employed in predictive maintenance applications. This research has received funding through IMOCO 4.E, an Excel project started in September 2021, involving 46 partners from 13 different countries. The aim of this project is to advance the intelligence and adaptability of mechatronic systems in the industrial domain. One of our case studies within the project centers on the monitoring of a cutting blade in an Acme Vega shrink wrapper and the detection of anomalies in its behavior. Our focus is to develop and certify trustworthy neural networks technologies for the detection of such anomalies. The reliability of neural networks in this kind of applications is crucial for the safety of the industrial system monitored. Furthermore, as previously mentioned, neural networks have been proved to be subject to adversarial perturbation. That is, small variation of the input of a neural network, like, for example, the ones caused by noisy sensors, may result in significant changes in its output, causing potential errors. Since the discovery of these reliability issues, formal verification has emerged as a potential solution, as it allows for the certification of the robustness of neural networks against this kind of adversarial perturbations. While a substantial amount of research has been conducted since the first paper on the formal verification of neural network in 2010, verifying current state-of-the-art neural networks remains highly challenging. Specifically, state-of-the-art verification methodologies lack scalability and are still unable to support the full range of modern neural network architectures. For instance, long short-term memory neural networks currently cannot be verified by state-of-the-art verification tools due to the extremely high computational complexity of the task. Now let me give some background on the model we considered. Autoencoders are a specific kind of neural networks designed to learn efficient representations of input data through an encoding-decoding process. The encoder component compresses the input data into a latent space representation, capturing its essential features. Subsequently, the decoder components reconstruct the original input data from this compressed representation, aiming to minimize the reconstruction error. Autoencoders can be utilized in anomaly detection tasks by training them on data that represents the normal behavior baseline of a system. Subsequently, the prediction error when processing real data can be monitored. A significant increase in prediction error, if the autoencoder was trained effectively, indicates a deviation from the baseline behavior of the system. This prediction error, often referred to as vector reconstruction error, can also serve as a quantifiable measure of the magnitude of the deviation. In our experimental evaluation, we considered the 1-year industrial component degradation dataset available on Kaggle, which consists in the recorded measurements obtained from various sensors for 1 year of operation of an Acme Vega shrink wrapper. The whole dataset consists of 519 recording sessions of 8 seconds, during which 2048 samples are gathered, for a total of 1,062,912 samples. The sensor considered focus on measuring the status of a specific cutting blade in the machine. The aim of the dataset is to showcase the degradation of the cutting blade to a point of failure, its substitution, and the following return to standard behavior. Clearly, the point of failure and the nearest sample to it represent our anomalies of interest. Unfortunately, the dataset is unlabeled, and therefore the point of failure and the related anomalous data are not known a priori. Since we need to train and test our autoencoders on baseline data, we choose to consider only the first 200,000 samples for our preliminary training and testing processes. The idea behind this choice is that it is unlikely for the cutting blade to be already degraded at the start of the operations. To ensure the correctness of our hypothesis, we further carefully analyzed the dataset. The remaining data are used in our experimental evaluation to further test the anomaly detection capabilities of our autoencoders through visual inspection of their plotted output. All the autoencoders we considered in our experiments present a similar architecture, which we show in the slide. All of our autoencoders present 3 linear layers with ReLU activation functions and a different number of neurons, followed by a linear output layer with identity activation function and a number of neurons equals to the size of the input of the network. The first autoencoder has 32, 8, and 32 neurons in the first, second, and third layers respectively. The second has 50, 10, and 50, the third 64, 16, and 64, and the last has 128, 32, and 128. The properties considered were instances of local robustness. This type of property formalizes the concept that, if a certain input is considered for a neural network of interest, small variations applied to it must not cause a great change in the corresponding output. This safety property can be formalized, as shown on the slide, by considering all the possible perturbation of the input whose infinity norm is bounded by a certain value epsilon, and imposing that the maximum variation of the corresponding output is bounded by a certain value delta. However, universal quantification makes verification undecidable. Therefore, we need to reformulate this property as its negation. That is, we need to check if there exists a perturbed input such that the maximum variation of the corresponding output exceeds the acceptable value delta. Here is a brief overview of our training setup. To train and validate our models, we utilized Pinever, a comprehensive tool designed for managing, training, and verifying neural networks. During our training process, we employed the Adam optimizer with the learning rate set to 0.001 over 50 epochs, using mean square error loss. We partitioned our dataset such that 20% was allocated for testing, and of the remaining data, 30% was allocated for validation purposes. The batch size was set to 512 for training and 128 for validation and testing. Following the training and testing processes, the whole dataset was used for a graphical evaluation of the vector reconstruction error. The verification process utilizes the over-approximate version of the algorithm provided by Pinever. This algorithm employs abstract interpretation to generate an over-approximation of the neural network's output for all potentially perturbed inputs relevant to our specific property. If this over-approximate output does not satisfy the negation of the safety property, it indicates that no unsafe data points were identified, thereby confirming the validity of the safety property. In this table, we present the results of our experiments. It is evident that all the autoencoders considered achieved satisfactory test loss. Interestingly, the larger models did not always outperform the others. Regarding verification, we assessed the 3 epsilon and delta values, corresponding to different properties and representing varying magnitudes of perturbations. Across all models and epsilon values, Pi never successfully verified the specified property within the 10 minutes timeout. However, it should be noted that not all the models were proven to be robust to the adversarial perturbations considered. In particular, AE1 and AE4 could not be certified to be robust in the case of the most stringent property. As previously anticipated, in this slide we show a graphical evaluation of the vector reconstruction error over the whole dataset. As can be clearly seen, the point of failure of the cutting blade occurs during the 4th month of operation, and all the autoencoders considered are able to recognize it. However, it is easy to notice that A1 seems to be significantly better at recognizing the anomaly. That is, its vector reconstruction error is significantly higher during the anomaly than during the standard functioning of the system. Currently, we are expanding our experimental evaluation by including more network architectures and additional verification methodologies and tools. Furthermore, we plan to explore more complex and significant input-output properties, and to investigate how to leverage the outcome of the verification process to actively improve the model reliability. Thank you very much for your attention.